Now we're going to focus on something called molarity. Molarity is a different unit. So instead of saying that the solution is a given percent, we could talk about this solution also in terms of molar units. Molar units are capital M. They're not referring to what's in your mouth. They're referring to moles. Moles being related to Avogadro's number of particles. So in molarity, the definition of that is how many moles of solute there is per liter of solution. So we're still keeping with the theme of solute over solution, but the units for molarity are specific to moles of solute and liters of solution. Brine is a salt solution. It's salt dissolved in water. In this case, it's used a lot in cooking. Some of you who have pickled before may know that you use brine to get the cucumbers to pickle, which involves some anaerobic fermentation as well. Here we have some chicken, which is brining in a solution of salt, and you can throw in there also some sugar and herbs and spices and citrus fruits, anything you want to flavor it with. And the idea behind brining is that the salt in the water moves into the tissues, thereby interacting with the proteins in such a way that salt moves into the protein, sort of massages it, tenderizes the meat, and also encourages water to flow in through a process we call osmosis. And in this process, it really adds a lot of water weight to the poultry. So when you cook it, it has added water, so it loses some water by cooking, but you've added water to the chicken so it doesn't lose as much water in the end and doesn't dry out. So brining is very popular. In this case, we're using 28 grams of salt and a total of 750 milliliters of this brine solution. So what's the molarity? Let's talk about the solute and the solution. The solute is NaCl, and the solution is called brine, which is NaCl aqueous. All the concentrations refer to the ratio between these. So all I need to do is figure out for molarity how many moles of NaCl I have and how many liters of this brine solution I have. So that's going to require some conversions, I think, because if you look at what we're starting with, 28 grams needs to be converted to moles. That's our solute on top. And then we have our volume of solution, which needs to go in the bottom, and that needs to be converted to liters because these are very specific units. So let's tackle the top part first. Okay, so I'm going to write it down here. So 1, we're going to convert grams of solute to moles of solute. To do that, we're going to need the molar mass, if you recall. 28 grams of NaCl is how many moles of NaCl? So we use the periodic table. We add up the atomic masses of NaCl, sodium and chlorine, and we should get 58.44 grams. And that is equal to 1 mole of NaCl. Alright, so we do that calculation, and we get 0.47912, blah, blah, blah. Of course, we always round this. We look at the sig figs we're starting with, and it's about 2 sig figs. Since this isn't our final answer, I recommend that we keep an extra decimal, which will help at the end. So let's go ahead and just keep an extra one for the purposes of our calculation. We're going to go ahead and just use this for now. And some people actually, because you're trying to round to 2 sig figs and you want to just carry an extra one, they make that last one sort of small to remind them that we're not going to use that later. Okay, so now we look at the second part of this. How many liters do we need? So we have 750 milliliters, and we want to convert this to liters. Alright, so this is where a lot of people get this mixed up. You must know the metric conversion. It's 1 liter, which is a bigger unit, is equal to 1,000 of these smaller milliliter units. Okay, you're going to see this so much, it's just going to become a part of your regular vocabulary. All right, so there we go. And the easiest way to do this math is just 1, 2, 3, right? Because you're moving it 3 places. Let's go ahead and now calculate the molarity. So step 3, the molarity is 0.479 moles over 0.750 liters. And we're going to round this to 2 sig figs because what we're starting with here has 2 sig figs in both numbers that they give. 0.6388. We're going to round this to 2 significant figures, so we get 0.64. And that's units of moles per liter, so you can write moles per liter or you can just write capital M. Now let's talk about orange juice. I go grocery shopping all the time and go through orange juice like crazy. So it gets really tedious to buy orange juice every day. Something that many of you might also do is to buy some concentrate. I know it feels like it's not as good, right? You could buy a ton of these little concentrate packages and then just add water and make your orange juice that way, right? And that's really convenient, particularly if you ride the bus or you walk to the grocery store like I sometimes do. So the way this works is that I start with something more concentrated, meaning the concentration is higher at the beginning. And then I end up adding water to it and making it dilute. Okay, the term concentrated and dilute are relative. That is, if I say that I have a 5% solution, that doesn't mean it's concentrated or it doesn't mean that it's dilute. It only has meaning when I compare it to something else. So if I have 5% and I end up with 10%, then the 5% is more dilute than the 10%. In this case, I'm going from a concentrated solution, actually called concentrate, and I'm adding water and diluting it to make it less concentrated. So if I were to try to look and see what the particles were, I would look at concentrate and see tons of particles packed in there because of the lack of water. And then when you add water, those particles are able to spread out. Okay? So that's the idea here. Again, we talked about concentration as percent, so I could say it went from a 10% solution and diluted down to a 5%. Or I could talk about molarity. I could say it was a 10 molar solution and now it's a 5 molar solution. Okay, and it doesn't necessarily have to go down by a factor of 2. It could be, 10% solution down to a 0.1% solution or something like that. It really just depends on how much concentrate you're using and how much water you're adding to it. And you want to be able to calculate these things, especially if you're looking to go into a field like healthcare where you're responsible for delivering a certain amount of medication in a certain amount of time, that kind of thing. You need to know, how much of this IV solution you have and how much of a drug to add to it and all this complicated stuff, right? So you need to know how to calculate these things. Let me just also say that concentrate in the chemical world is called a stock solution, because chemists make lots of solutions, and those stock solutions are really handy because we could grab a stock solution, take a little bit of it out, add water to it, and make whatever dilution we want from it. So I have a conceptual question for you now. Which solution has a higher molarity? On the left, I have a volumetric flask that's only about half full, so the volume is 100 milliliters. And let's say there are, of course, there are millions of particles in there, but I'm just going to write that there's 5 particles. On the right, we're visualizing 10 particles, and now the volume is 200. So the question is, which solution has a higher molarity, or which solution has a higher concentration? Go ahead and pause the video and think about this, and when you have an answer of solution A or B, go ahead and unpause it. So in this case, we have 5 particles. Remember, the solute over the solution. In this case, for solute we have the number of particles, and for solution we have the volumes. So if you went ahead and calculated this out, you would see that these numbers are actually equal. So even though we have less particles in A, the volume is also less. So it turns out that when you double the particles and double the volume, that you're actually keeping that ratio the same. Neither is the answer okay, or both. A concentration of A equals the concentration of B. All right, let's try a dilution calculation. And in this situation, you're going to draw out from the question all the things that you're starting with. And it can get a little bit confusing because we have two situations going on here. All right, we're starting with a solution that's more concentrated, and we're adding water to it, and so we're going to get a solution that's more dilute. All right, how do I know that? Is because this is a dilution problem, and you're adding water to change the concentration of a solution. So I like to divide this into two parts, what I have to start with and what I have to end with. There are four pieces of information you're going to need to do these dilution problems usually. You need the concentration of the solution you're starting with and the volume you're starting with, the concentration you want to end up with, and the volume you want to end up with. And you're usually going to be given three of these four in order to solve. So we've got C1 is the concentration we start with, C2 is the concentration we end with. They want to know what's the molarity of the new solution. Molarity is concentration. So I'm going to say we don't know what the new solution is going to be in terms of molarity. But we have all the other information. So let's draw that out. Some of this information is already chunked together. So that tells you that those are referring to the same solution. So the volume is 100 milliliters of 10.00 molar solution. And then we're diluting it to 250 milliliters. And we're going to use this fancy glassware here called a volumetric flask. And the way that these work is when this line is etched into the glassware. And when the water is filled to that line, and you're mixing the solution the whole time to get those particles in there, then you start filling it slowly to the top. That is 250 milliliters, very precisely. So let's go ahead and calculate what this is. If you think about this conceptually, here are the particles that we're starting with. And I'm adding water up here. I'm adding water to that solution. Are the number of particles going to change when I just add water to this? Okay, so I have 10 particles in there. Are any particles going to leave, or are any particles going to join them? And the answer is, as long as this is pure distilled water up here, the answer is no. Just water is going to add in there. So I'm still going to have my 10 particles, but they're going to be more spread out. The only difference is that I'm going to have more water in here. So that makes the volume much higher. Thus, the concentration decreases. Because the number of particles is the same, the number of moles on this side of the equation is going to equal the number of moles on this side of the equation. And so in order to calculate moles, if I would basically multiply those two together and multiply these two together if the volume was in liters. Okay, so let's go ahead and just write that. If these were multiplied together, and if these were multiplied together, assuming that the volumes were in liters, then that would become moles. And so just a little demonstration of that is concentration is mole per liter and volume is liters. So you can see how it would be moles on both sides, right? However, because this is in milliliters, we can either convert it to liters and this will work, or you can take note that milliliters would be on both sides of this equation, thus they would cancel out. So we actually don't even have to convert this to milliliters. So let's go ahead and solve this. Concentration C1 is 10 molar, or I'm going to go ahead and just write moles per liter multiplied by 100 milliliters equals C2, which we don't know, times V2, which is this. So all the numbers plugged in looks like this, and I'm going to divide both sides by 250. So the final volume is 4 molar. Let's go ahead and take a look and see if that makes sense. If we're starting with 10 molar, and let's just say to conceptualize this, we have 100 milliliters to start with, and let's say that instead of 250 we make it 200 milliliters. If we go from 100 milliliters to 200 milliliters, then we're basically diluting it in half, right? So a 10 molar goes to 5 molar. Since we're adding a little bit more water than that, it's 250, not 200, then the concentration should go down a little bit more. So instead of 5 molar, the answer is 4 molar because it's 250 milliliters, not 200. So the strategy in this problem is to recognize that we're looking for moles, we have volume, and we have molarity. So this is just a molarity problem. So write your equation. Molarity is moles of solute per liters of solution. Okay, and we actually have the molarity. We have milliliters, which can be converted to liters, and we're looking for moles. One thing you could do is just recognize using algebra that if you multiply both sides by liters, then that should pretty much help you solve for moles right there. Another thing that, okay, so let's write that down. Moles equals molarity times liters. Another thing you can do is when we did density, okay, we use this little triangle as a tool here. Molarity equals moles per liter. And so if we're looking for moles, you cover up moles, and you see that molarity times liters will get you moles. Okay, so that's a little tool that you can also use just to double check your algebra. So all I need to do here is I need to multiply molarity and liters. So my molarity is 3 moles per liter, or molar. I like to write capital M out as moles per liter so that I can apply a little bit of dimensional analysis here. 5.25 milliliters. So notice that I should have converted that to liters so that it would cancel out with the liters down here. So what I'm going to do is I'm going to rewrite this, but I'm going to have converted the milliliters to liters. So I'm going to convert this by moving the decimal place over 3 places to the left. Now I can see that my units cancel out and the answer comes out to this long thing here. And then 3 sig figs to start with. Both of these numbers have 3 sig figs, so I'm going to round this to 3 sig figs. And the unit for this is moles, and this is KOH. Another way to solve this without algebra is to just use dimensional analysis. Okay, so just keep practicing your dimensional analysis skills, especially for some of you guys going into healthcare. You're going to have a lot of dimensional analysis type problems, and it would just really help you if you understood that. So if we look at the problem, how many moles are in this much of that? Notice that the molarity is a conversion factor for moles per liter. Okay, so if you look at capital M and you just write moles per liter next to it every time you see it, then you should recognize that that's a conversion. And this is what I'm starting with. So I'm going to write that down. So this is what I'm starting with. Okay, and I have that conversion, moles per liter, but I also know that I need to put milliliters down here for it to cancel out. So I'm going to need to put in another conversion so that I get moles per liter and the liters cancels out. So what goes up here is the liters. So I do that conversion first, and then I do this molarity goes here. Okay, and then I can pretty much see how dimensional analysis works out as well. This is a really good skill to practice any chance you get in this class. And it should give you the same answer.